Okay, so this is video number 2, and in this video we're going to have a look at a concept called net force. So, let's get straight into it. Okay, so net force, this is the idea. We've started to look at some force diagrams. Net force is essentially just means total force. So we've said forces can have both sort of size and direction. So for this first one, if we this first problem on the left here, if we have a force due to, say, gravity pushing downwards, that's 800 newtons, and a tension force, I think the tens here is short for tension, so maybe there's a rope on this box and it's hanging from that. If the tension force is 1200 newtons, what is the total or the net force? So essentially, if forces are acting in opposite directions, we can basically subtract one from the other. So here we can say 1200 minus 800 is going to equal, so essentially we're going to have 400, alright, and the total force, because it's bigger going upwards, so it's 400 newtons in the upwards direction. So we can see here for this first problem here, it's 1200 take away 800. The total force, or net force acting on this object, will be 400 newtons upwards. So I'll just clear that. Alright, so this next problem here, we've got 600 acting onwards. So this object's probably a ball or something that's falling through the air. The force due to gravity is 800 newtons, and the force due to air resistance is 600 newtons upward. So what is the total or the net force? So again, we just work out the difference. So in this case, that's 800 minus our 600. So we can always just take the bigger number minus the smaller number. And in this case, so that obviously equals, we've got 200. Alright, and so which direction is this? Well, because the force downwards is the bigger one, this is 200 newtons downward. So it's important just to remember here that forces have both a size and direction. So we should technically always be including the direction of the force. Alright, now my third problem here sort of looks a little bit more complicated because we've got 3 forces, but let's have a look. So we've got 50 newtons acting upward, 50 newtons downward. So the total here, the total or the net force up and down is 0. And then we've got 20 newtons acting to the left, and nothing acting to the right, so our net force is 20 newtons to the left. So we've got 20 newtons to the left. Okay, so net force, essentially you're just working out the total, and if you've got the forces acting in opposite directions, you can subtract the smaller one from the larger one. Now, some problems might have several forces acting in the same direction, so we could add another arrow here, and if this arrow was 100 newtons, should have probably done it a little bit bigger, then we could say, well, the total upwards is 150 minus the total downwards, which is 50. Our total force up would be 100. So any forces acting in the same direction can be added together, and those forces acting in opposite directions can be subtracted. Alright, so let's have a look at another problem. Sorry, just get myself sorted here. Okay, so here we've got a box with some forces acting on it. You'll notice this time the arrows are pointing in towards it. Convention, kind of most of the time these days we prefer, or it's probably best if you draw the arrows coming from the center of the object outward. So normally we would have put the 3 on this side pointing out and the 5 on that side pointing out, but it's not too important. So anyway, let's have a look at this. We've got, what's our total or our net force in this situation? So I've got 5 acting this way and 3 acting this way. So what's the net force left and right? Easy peasy. So we've got 2 newtons, 5 take away 3 is going to be 2 newtons in this direction. Alright, fantastic. Now I'm also going to have, if we look at my arrow here, I've got 2 newtons, so I should do that roughly the same size, 2 newtons acting upward. So for year 11, that's totally fine. For this, we could say that the net force here is 2 newtons up and 2 newtons across. And that's perfectly fine. That's totally legitimate. But some of you might already be able to see, or if you're a clever cookie and you're pretty good at maths, you should be able to see that you could actually work out what the overall force is. So this involves a little bit of Pythagoras. So if we've got 2 over here, and we've got 2 going up this way, 2 newtons up this way, you can actually work out. Now, it makes sense if you think you've got 2 newtons pushing across to the right and 2 newtons going up, the overall kind of force or motion might be in this direction. So this box is going to start moving. It's actually going to start speeding up to the left and to the right, means it's going to end up kind of moving over off in this direction. And we can work out the size of the force if you do your Pythagoras, where you take 2 squared plus 2 squared and square root the answer. All right, you can work out, you can imagine if this was a maths problem where we said work out x, that's a terrible x, but if we worked out what the diagonal is here. All right, now you're not expected to do that in NCEA Level 1 Science, but some of you, I'm sure, are more than clever enough to be able to work that out. Okay, so next problem. Oh, skipped a bit. All right, there we go. All right, fantastic. Oh. Okay, so my first problem here is basically we've done this a little bit back to front, and that's what you just have to be aware of. It's the same idea, but we're kind of working a little bit back to front. We've told you the net force is 0, so that would mean 0 in all directions. We've got a net force of 0, so what must the force at A and B be? Well, A must be equal to the left here, it must be equal to 50 newtons on the right. So A must be 50 newtons, alright, to have a net force of 0 horizontally, and B here must be 200 newtons, so that we have a net force of 0 up and down, alright, vertically. So see it here, if we have a net force of 900 going up, what must C be here? Well, let's think about it. If I had 900 up here, well, we'd have to subtract 200 from it. We'd only have a net force of 700. So we're actually going to have a net C here must actually be 1100. Must be 1100 newtons. Oh, sorry, that's 11,000. There we go. 1100. So that 1100 take away 200 is going to give me my net force of 9. So we can actually work this out. In this case, we're actually adding, we're taking the 900 plus 200 gives us the 1100 up here. So, some of you will find it easier just to think of it in terms of what number here minus 200 is going to give me the net force of 900. Okay, so this needs to be 1100 newtons. Take away the 200 gives us a net force of 900 newtons up. Now normally we'd try to show this with arrows that kind of reflect the size, so this arrow at the top should be a lot bigger, but in this case I think they're focused just on the values, trying to get you to work that out. So if you were drawing arrows, try to keep them make them represent the actual size of the force. Okay, so simple enough. Now we're going to talk about, well, we can work out the net force, the total force is easy enough. What does it mean in terms of the motion? What happens to an object when there's a net force applied to it? Well, let's start off with, and this is probably one of the really key ones, what happens when there's no net force? Well, if the forces in every direction are equal, then we say the forces are balanced. So the force on this side is if the force on this side, the frictional drag, is equal to the applied force, the forces are balanced. Now, this could occur if we imagine in this example that this car is going, 20 kilometers per hour. So really slow, just in a car park or something. Well, might be a little bit fast for a car park. We'll go 20 kilometers per hour. What would happen if the forces are all balanced? Well, lots of people might say, well, if there's no net force, there's no net force, won't it slow down? Well, actually, if there's no net force, objects will continue moving at a constant speed. So the important thing to remember here is we've said that forces can change the motion of an object. So if there's no net force, the motion of the object can't actually change, so it will continue at a constant speed. It actually requires, it takes a force, you would need a force, a net force, to slow the car down. In the same way, you would need a net force to make it speed up. But if you have no net force acting on it, it's going to carry on at a constant speed. Now, the reason why that's sort of hard to picture or imagine is that friction is something that kind of plagues us here on Earth, that we can't really get rid of the friction. We can try and reduce it, but there's always going to be some friction. So unless we put some force forward, well, we're always going to have this friction that slows us down. We're always, so if we've got no applied force or thrust, then the friction's obviously always going to be bigger than our zero force, and it's going to make the object slow down. But if there wasn't that friction force, it would carry on at a constant speed forever, forever, and forever. And that probably actually makes a little bit more sense if you imagine, rather than a car on Earth, right, if we imagine something in space. Now, it was actually Newton who came up with this idea. This is actually Newton's first law, and often we say, an object in motion will stay in motion. And he also said an object at rest will stay at rest. But as I was saying, it's often easiest if we imagine something traveling through space. So I've got this picture, and sorry it's a bit blurry, but this is Bender from Futurama, and comes from an episode where he's shot out of the Planet Express, the spaceship, and because he's going faster than the spaceship, they can't catch up to him. So here's Bender for almost, for the majority of the episode, floating through space at a constant speed forever, forever, and ever. And it's a good example of, if you think of objects in space, they'll keep moving at a constant speed. Their motion won't change unless a force is applied to them. So unless a force is applied to slow them down or speed them up, they keep going at a constant speed. And so when you do your force diagrams, you've got to remember that if the forces are balanced, the object will continue at a constant speed. Now, if it's stationary to begin with, if it's not moving and there's no net force, it will continue at a constant speed of 0. So being stationary, an object that's stationary is actually traveling at a constant speed of 0. And if there's no net force, it will continue to move at a constant speed of 0. Alright, so what happens when the forces are unbalanced? Well, if the forces are unbalanced, if we put our foot down on the accelerator and provide a little bit more thrust forwards than the friction or the drag force pushing us back, then the object will actually accelerate. It speeds up. At the same time, if we take our foot off the gas and the drag would become bigger than the thrust force forward, then we're going to decelerate or slow down. And this really is that key idea. It's the same idea as the one at the top. Essentially, it takes an unbalanced force, it takes a net force to change the motion of an object. And when we say change the motion of an object, it can either cause it to change direction or speed up or slow down. If the forces are balanced, it will continue, its motion, it will continue in a constant motion. So this is essentially Newton's second law, where he said acceleration is proportional to the force applied. So if you apply a net force to an object, if there's a net force being applied, that's proportionate to its acceleration. If we apply a small net force, it'll accelerate slowly. If we apply a large net force, it will accelerate much more quickly. So here's the question that always trips students up. And it's a little bit tricky because, you'll see in a second. So the question that often trips people up is this one. We look at a ball, let's say, it's been thrown in the air. So this ball is traveling through the air, and let's say it's flying upward. Now, I'm not interested in what was happening down here when the hand was pushing it, but when it's actually on its way up in the air, so it's in the air traveling upward, what forces are actually acting upon it? Well, essentially, we've got the force due to gravity. So this is the weight force. And we might have a small force of air resistance, which would be against the direction of motion. So it would actually be in the same direction. We would have a little bit of friction or air resistance pushing it downwards too. Now this seems really kind of counterintuitive. It seems really crazy that the ball's moving up, but the only forces acting on it are down. Well, there's nothing really wrong with that at all, because we know if we throw a ball into the air, what's actually going to happen? Does it just keep going up and up forever? Well, no. The ball, as it goes up in the air, it slows down, and eventually it reaches comes to a stop for a fraction of a second, and then it starts to fall back down. So it's these forces here that are actually causing the ball to slow down. If it wasn't for these forces, if it was in space, the ball would carry on moving away from us forever and ever. So although the ball is moving upward, the only forces acting on it are downward, and they're what are actually causing it to change motion, causing it to slow down. So what happens on the way back down? Well, on the way back down, we've still got the weight force. That's actually what's going to make it accelerate downward. So on its way down, it's going to speed up or accelerate downward because of this weight force. Now, on the way down, the air resistance, remember, always opposes motion, so we'll get a little bit of drag or air resistance in the opposite direction now. We'll get a little bit of air resistance acting upward. Now, they often like to ask questions like this in the exams, although they'll often ignore the drag. They'll often ignore the air resistance or drag completely. You'll get a question that says, pretend there's no air resistance or drag or friction. And really what they want to see is that you understand, well, while the ball is in the air, so we're not talking about when it was touching the hand, but once it's in the air, the only force that's really acting on it is the weight force downward. And that's why if it's moving up, it's going to slow down, and eventually it slows down right to a stop, and then it starts to actually accelerate downwards. Okay, so here's an actual exam question. So we've got an actual exam question here, an NCEA exam question. And essentially it says, now there was a bit leading up to this, so I've sort of taken this out and added enough information here so that we can actually do it. But it's based on an NCEA question, nevertheless. So what it's asking you to do here is to use arrows to show the directions of the thrust and friction forces. Beside each diagram, state if the thrust is greater than the friction, the thrust is equal to the friction, or the thrust is less than the friction. So if we have a look here, we've got my runner. If he's accelerating, it means the force forward must be bigger than the force backward. So we're essentially saying, and I should label these, but I'm going to be a bit lazy. So essentially saying for this first one, all right, that the thrust force is greater. So if we've got a greater thrust force, he's going to be speeding up. And we know that's true. If the forces are unbalanced, it's going to accelerate. Now, section B here, this the runner here, if he's moving at a constant speed, then the thrust force must be the same size as the friction force. So in this case, they're the same or equal to. And that's, if he's moving at a constant speed, his motion isn't changing, the forces must be balanced. And that's the one that always trips people up. They think he's moving forward, there must be a force forward. Well, think of Bender in space. Okay, so in space, if there's no forces acting on something, it can still drift. So a constant speed means the forces are actually balanced. Alright, let me clear that so I can drag it up. So section C, if he's decelerating. So what does decelerating mean? Well, it's a fancy word for basically saying he's slowing down. So if he's slowing down, again, the motion is changing, the forces acting upon him must be unbalanced. So in this case, oh, sorry, that's a mistake. In this case, the thrust forward must be less than the friction force or drag. And this is your typical example. This is the reason why if a car, if you take your foot off the gas completely, why a car slows down. Because there's more friction or drag and there's effectively no force pushing it forward. Alright, so in this case, if you've got a smaller thrust force than the friction or drag, you're going to decelerate, you're going to slow down. So I think the moral of the story here, so in this case it was the thrust force is less than the friction or drag. So I think the moral of the story here, what you've got to realize or try to remember, is essentially that if you've got an unbalanced force, if you've got a net force being applied, that the object will accelerate or decelerate. It's going to speed up or slow down. An unbalanced force always changes the motion of the object, so that it's either going to speed up, slow down, or change direction is technically another option too. If the forces are balanced, it will continue, the motion will continue unchanged. So if the forces are balanced, it's either going to be stationary or it's going to travel at a constant speed, continue to travel at a constant speed. And, to be honest, being stationary, something that's still, is actually just traveling at a constant speed of 0. So remember, unbalanced forces, you get acceleration or deceleration, or it changes direction. Balanced forces, or no net force, means it continues at a constant speed. Hope you found that helpful.